Okay, hello everyone. In this video, we are going to discuss about LCR circuit. That means we are going to solve the LCR circuit to find out the current, uh, instantaneous current in the LCR circuit using Laplace transform. In our last class, we have been discussed uh, RC circuit. This class, we are going to discuss LCR circuit in detail. Okay, so let's start. From figure, you can see that L's inductance, capacitance, and resistance connected with series. Consider LCR circuit is connected with EMF. So here LCR circuit means three elements are connected with each other as series, and a EMF is connected with this circuit. Here applied voltage is a impulse or instantaneous. For a short time period, this E will be applied then removed. So only for that it is written as impulse or instantaneous. Only for that E can be represented as E into a delta function. As we know that if we are going to consider a delta function exists at a particular point. So ideally delta function is your like this. At suppose at A it is exist, or at 0 it is exist delta function. That means at 0 it is maximum, and other points it will be 0. That means delta t will be equal to the so-called infinite at t equal to 0 and 0 elsewhere. That means at t equal to 0 it exists, otherwise it is not, does not exist. So here instantaneous applied voltage is represented as E into delta t, where delta t equal to infinite or maximum, you can say maximum infinite at t equal to 0 and 0 elsewhere. If suppose we have delta t minus a, then the value exists at t equal to a. Okay, so infinite will be at t equal to a, 0 elsewhere. Okay, so here delta only t means delta t minus 0 is there. That means delta function exists at t equal to 0. Delta t minus a means delta function exists at t equal to a. At t equal to a, the value is exist or infinite we can say, and otherwise it will be 0. Okay, so now the instantaneous voltage drop across LCR is your L into di by dt, across C Q by C, across R I R. When I, instantaneous current, is going to flow through this circuit when for a short time period, or instantaneous voltage is going to be applied, right? Now we are going to solve. Now we are going to consider KBL rule, Kirchhoff's voltage law. All the voltages dropped by all the elements will be equal to applied EMF. So L into di by dt plus Q by C plus IR equal to applied voltage is your E into delta t. Let this is your equation number 1. Now we are going to apply Laplace transform. Both the side of this equation number 1, we found Laplace transform applied on this one, Laplace transform on Q by C, Laplace transform applied on IR, Laplace transform applied on this one. So here L is constant, get taken outside. Laplace transform of first derivative di by dt, first derivative, so it will be s into Laplace transform of I, which is the function of t, minus I at t equal to 0. Okay, plus here 1 by c constant, q is written as 0 to t I dt, r into Laplace transform of I, which is the function of t, is equal to, here you can see here Laplace transform E into delta t. E is the constant, or Laplace transform E delta t in general we can write 0 to infinity e to the minus st into E delta t into dt. Okay, so here we substituted I bar instead of Laplace transform of I. So here instead of this one we have to write I bar, and I at t equal to 0. T equal to 0 means current is not flowing through the circuit. Here t equal to 0 means there is no uh, connection of your applied voltage. That means no closed circuit, we are no closed circuit that we are going to consider at t equal to 0, right? So hence uh, at t equal to 0 there was no current we can found in the circuit, so I will be equal to 0. remember it, when t equal to 0, that means the key is not closed. Here I drawn a key, suppose the key is not closed. When t greater than 0, key has been closed. So when t equal to 0, I will be equal to 0. I will be equal to 0. Here 1 by c, and we know that Laplace transform of a integral. Laplace transform of integral is nothing but 1 by s Laplace transform of f of t, that we discussed in our last class, or in previously also we discussed that Laplace transform of integral, that is 0 to t f of t dt, is your 1 by s Laplace transform of f of t. Same thing it has been written, and also I here I written that this value Laplace transform of integral 0 to t I dt is nothing but 1 by s Laplace transform of f of t by using Laplace transform of integral. And here I r, Laplace transform of I is your I bar, equal to e into 1. Why 1? Here you may remember that 0 to infinity f of t into del t minus 0 value into dt equal to f of 0. This is the one of the property of the delta function. That means, or we can say 0 to infinity f of t into delta t minus a dt equal to f of a, right? So here if I'm going to compare this equation with this equation, so here e to the minus st, see here e is the constant taken outside, so here e to the minus st into delta t dt, here f of t delta t dt, here delta t is there, means t minus 0 you have to consider. So e to the power minus st is nothing but your f of t, right, will be equal to how much? That means e to the minus st into delta t minus 0 dt will be nothing but e to the power 0. Here f of 0, according to this property f of 0, here f of t is nothing but this one, this value. So instead of t, if I will put 0, so e to the 0 will be equal to 1. So integration this one, integration 0 to infinity e to the minus st delta t dt will be 1 and e taken outside. Okay. Here you consider L by S I bar taken common from this term, and this term. We found a square plus r by L into S plus 1 by L C equal to E. Consider r by L equal to 2a, 1 by L C equal to a square plus b square. Just substitute over here. So this will be and this L by S taken this side will be S by L. Okay, so I bar is there, I bar a square, r by L considered as 2a, 1 by LC considered as a square plus b square. Okay. Now I bar, that implies I bar will be equal to, this term will be divided with RHS. This whole term will be divided with RHS, ES by L into this much. Okay. Or E by L is the constant written separately, S by this much. So the numerator can be modified as S plus A minus A. This one can be written as, here this a square plus 2as plus a square can be written as s plus a whole square, and this b square is b square. Now e by L into s plus a by this whole denominator minus a by this one, right? Now we are going to take the inverse Laplace transform of this equation, that means left side and right side. Inverse Laplace transform of I bar, inverse Laplace transform of this and this. E by L is constant taken outside. Inverse Laplace transform of s plus a by s plus a whole square plus b square, means it is straightly, suppose we have s by a square plus b square, that means cos bt will be answer. But s plus a will be there means fast shifting theorem we have to put. So it will be e to the minus at cos bt. And likewise here s plus a whole square plus b square is there. So we have to multiply one b over here and divide one b. Then we can found the answer e to the minus 80 into sin bt. Already a is there. So a by b. By using fast shifting theorem, I have to write over here. By using fast shifting theorem or property, we found this value and this value. Okay. Now e to the power minus 80 taken outside, it will be e by l cos bt minus a by b sin v2 into e to the power minus 80. This will be the answer for LCR circuit. Thank you so much for watching this video. In our next class, we are going to discuss simple harmonic oscillator. Okay. Thank you.